Hi, so this is development of a low-cost network of street-level flood sensors, also known as FloodSense, and this is our final video presentation. My team includes myself, Nama, Carolina, Deja, and Ethan.
So our project goals for this project were to create 5 flood sensors, test sensor connectivity outdoors, install 5 flood sensors, build a web portal, and to demonstrate real-time data from flood sensors and a dashboard using open source tools such as Grafana. And what we were able to implement within the time frame was to build 3 flood sensors, test sensor connectivity, build a web portal, and demonstrate real-time data from the flood sensor and the dashboard using tools such as Grafana. So the reason we were not able to build 5 flood sensors and we built 3 instead were to limited resources that we had. We did not have enough hardware components that we needed to build 5 flood sensors. And once we ordered them, they were actually going to arrive 2 weeks before the showcase, which was not enough time to build the 2 extra flood sensors because we were focusing on other things that took priority in this project. And another thing that we did not get to do was to deploy our flood sensors outdoors. So the reason we were not able to do this was because we did not have a working router. The router was needed to connect the flood sensors to the internet so that the sensors can transmit their data over the air to our web application. We were having troubles with the router connecting it to the internet, and we found out last minute that the reason the router wasn't working was because the router modem was not compatible in the USA, only in Europe. And it was such a last minute thing that we figured out that if we were to order a new router, it wouldn't have came in time for the showcase. So due to not having a router and due to time constraints, we were not able to deploy the sensors outside. However, we were still able to test sensor connectivity by connecting the sensors locally to our computer and using a Python script, we grabbed data from the computer's USB and sent it to the Helium network, which the Helium network is a network of public LoRa gateways that we were able to connect to. And then once it's on the Helium network, we can send that to AWS via MQTT, and we can send that into our database. And that was how we were able to view in real time the data from our sensors to our dashboard. So although we had certain goals that we were not able to meet, we were still able to overcome those challenges and find a solution around the things that we did not have due to things like time constraints and not having certain components.
Now I'm going to talk about our project implementation and how we went about developing these sensors. So it was a bit tricky because we wanted to work all together step by step, but after realizing that each step will take time and relies on the other, we decided that we would split it up into 4 different pieces, and these are the main pieces of the project. This includes the hardware, which is building and coding the 5 sensors, data, which is actually retrieving data from the sensors and putting it into a database. This goes along with the pre processing and any type of streamlining we need to do. Then we have the Grafana dashboards in the front end, which kind of go hand in hand because the Grafana dashboards sit on the front end. So those two members work together on developing that and deploying it. Each of these roles had a crucial part in our final product. I worked on the data, Deja worked on the hardware, Carolina worked on Grafana dashboards, and Ethan worked on the front end.
So I'm going to go over some of our project requirements and constraints that we had, both on the hardware side and the software side. So on the software side, we needed to have a map with markers that led to the dashboard page. We also needed to have a dashboard page that displayed graphs for that sensor that refreshed on their own. We also needed to be able to view other sensors and time ranges in the dashboard page. And of course, we needed a front end design. So the main kind of thing that we needed on the software side was regarding full stack web development, and it was being able that we had a dashboard that had a map with all of our deployed sensors. And when you clicked on a sensor, you can see the data, the real-time data from that sensor that refreshed on their own. People needed to be able to view other sensors and edit the time range with that sensor. So whether if they wanted to see it within a 24-hour period or with a 1 hour period, a 1 month period. And overall, just made sure we had a nice front end design that was user friendly and easy to look at. Now, on the hardware side, we needed to have weather resistant housing for all of our electronic components, such as our sensor and our microcontroller. We also needed to have, or we needed to be able to accurately read distance every few seconds. So this is something that we would do within the sensor firmware itself. And then we needed the sensors to be able to connect to the internet and cloud, and also needed them to transmit data over the air to our cloud applications via the LoRa protocol. So the main kind of idea with the hardware is that it needs to be able to be in a weather-resistant housing because, of course, these are going to be deployed outside where it's going to be raining and where they're going to be measuring the water levels of floods. So it's really important that they won't get damaged by any water. And then also we needed to be able to develop the firmware for the hardware to meet certain requirements, such as read distance and read it accurately every few seconds, so that way we can accurately show that distance on our dashboard, and also connect to the internet and the cloud, so that way we can transmit the data over the internet to the cloud. Because if we're not connected to the internet, then we can't transmit data to the internet. So that's something that we would do in the firmware of the actual sensors. And once it's connected to the cloud, we can code to tell the sensor to send this certain amount of data or this kind of data over the air to our cloud applications where it can then be analyzed and sent to our dashboard.
Hello, so this is our project design, at least on the software side. And for our front end, we decided to use a framework called React. And for our back end, we decided to use a language called Go, and specifically their Gin server package, which is pretty easy to use and set up for endpoints and stuff like that. Speaking of which, we created two main ones. One is called Get Sensor IDs, which is called on the Mapbox map page, so that it only not only retrieves sensor IDs, but it retrieves the longitude and latitude for every sensor that's set up, and in InfluxDB so that on the map, we're able to create markers where each sensor is located based off their longitude and latitude and take the sensor IDs and send them to the dashboard page. And we also have the create new dashboard endpoint, which could be used in the Telegraf during pre-processing so that whenever a new sensor is set up, the graph creation process is automated so that they can just call this endpoint and a new dashboard is created in Grafana with the sensor ID. That's why I take sensor ID as a parameter. Um, and then it creates 6 new graphs, one for the past 24 hours, one for the past 7 days, 3 months, year, and one for the current and depth at the current moment of the water of whatever it is. And right, so the endpoint gets creates a new dashboard, automates that process so that in the front end, all we have to do is create the import link. So the way Grafana imports graphs into front end is using iframes, and they don't have an endpoint in their API, in the Grafana API, that allows us to retrieve the iframe link for the graph in our dashboards. So what I thought of doing was I noticed that every iframe link basically follows the same structure. It goes with the initial URL, domain name, and then it has the organization ID, dashboard ID, which is going to be the same for almost all of these. So what I did is I changed the dashboard name to sensor ID so that I know which dashboard it is because I'm on that specific ID. And the only thing that changes is the panel ID and then the dashboard ID. So I was able to, every time we need a new graph, once you go onto the dashboard page, it creates the 6 links that we need so that no API is called, just those links are created in the front end. So all in all, an endpoint is only called once in the entire like lifespan of like on that being on that website, which makes things pretty efficient. And then for deployment, We use EC2 instances to deploy, so we deployed Telegraf and InfluxDB on one instance, Grafana on another, and then our front end and back end on another. And for our front end and back end, we both had them on one instance, and we used Nginx to reroute the ports, so the front end is displayed on the main port of the website, and we use PM2 to run both the processes at the same time, especially once the instance is closed, so that they continuously run. And we use Serpent and Let's Encrypt to get an SSL certificate, which is pretty simple to use and set up. And that allowed us to have our front end be floodsense.org, rather HTTPS FloodSense.org, but then that did cause problems because I was trying to call Grafana, but we got a mixed content warning because you cannot have an HTTPS site calling stuff from HTTP. So I had to go back and get an SSL cert for my Grafana instance. So then I went back, got a domain name and an SSL cert for my Grafana instance so that then my front end can communicate with Grafana and vice versa. And then overall, we ended up with HTTPS for our site, floodsense.org. And yes, our sponsor used GoDaddy in order to buy the domain name and set up all the DNS settings. And so, yes, that's sort of the structure that we went with for our project and the architecture.
Hi, so this slide is going to be talking about the web application. So previously, like Carolina was talking about in the previous slide, the front end was built with React. Now talking about the styling of the actual website, I use Tailwind CSS to pretty much use as a framework to develop the front end. Then we used Mapbox as pretty much our map integration for our application. And the biggest hurdle that I think I had was actually just switching from Material UI, which we originally had as our CSS package, to Tailwind. So that's pretty much what this is about. And then later on, I'm going to show you a demo of the actual application.
So I'm going to talk a little bit more about the project design regarding hardware. So there were three main aspects regarding hardware design, which was the PCB, the ultrasonic sensor, and the assembly of the sensor in general. So for the PCB, I used the KiCad software to print and design the PCB. So we needed a PCB to mount our components such as our microcontroller, ultrasonic sensor, LoRa antenna, etc. And it needed to be a certain size and shape in order to fit into our housing. So one thing that I noticed with our PCB after it was printed was that it was not connected to ground. And I realized this because after testing the voltages and the continuity of the PCB and the hardware components as I go, I realized that the microcontroller would not turn on, and it was doing this because it was not receiving the correct voltage, and that led me to realize that the PCB was not grounded correctly. So in order to fix this, I added jumper cables all over the ground connections on the PCB that stemmed from the ground input of the battery, and that solved my problem, and it made the PCB grounded all over the ground connections. So by doing that, I was able to successfully assemble all of the hardware pieces and make sure they were connected correctly. And now talking a little bit more about the ultrasonic sensor. The sensor has 4 connections. 2 of them are for power and ground, which is connected to the PCB, which is then connected to the microcontroller. And the other 2 are to read distance and the output the distance. So the way that the ultrasonic sensor works is that it reads distance by emitting high frequency sound waves, and it measures the time of flight of those sound waves. So the way that this sensor outputs the distance is through serial format so that we can see that in the Arduino code. And now the last part is just assembly in general. I soldered all of the materials onto the PCB, and throughout the way I just made sure to use a multimeter to ensure the continuity of the connections throughout the assembly process. And I just did that by making sure there was continuity and that the voltages were correctly showing on the multimeter. And throughout that process, I was able to connect or assemble 3 sensors and also develop the firmware for the sensors that connected to our cloud application.
This slide covers our project testing and how we went about testing each part of our project. To start off, I'm going to talk about the sensor connectivity to the Helium network. This involved going to a hotspot area on the Helium network and programming the sensor and trying to connect to this network. We tested the connectivity in multiple places, including FAU and a coffee shop, realizing that FAU was not in the network. Once at the coffee shop, we were able to connect and see data forming on the ChirpStack UI. Then we tested sensor accuracy and readings. So in the video, I have a dashboard with the sensor's readings, and then I have a ruler with the distance of the sensor, showing that the sensor is reading 300 millimeters, and in fact it was 300 millimeters or 30 centimeters away from a wall. We also tested the sensor from a higher distance, and here you could see we had the sensor sitting on a around 6-foot pole, and we had a bucket filled with water, and as we filled the bucket with water, we saw that data was increasing and the numbers were increasing. And then as we removed water from the bucket, we saw the data decreasing. We also tested our endpoints, our API endpoints that we created, which are for graph creation and getting sensor IDs. We tested those using Postgres.
So in this slide, I'm going to be talking about the discussion and pretty much the lessons that we learned from this project. So one of the first things that I learned was when we were hosting the application, AWS was charging us a lot of money. So having to manually install and manage things like certbot and let's encrypt for manual setups like SSL and creating like HTTPS for free instead of using things like CrowdStrike or I think it's Cloudflare to give us those HTTPS protocols and actually working around those things to create things for free was one of the first things that I learned. Another big thing that we learned as a group was just the importance of planning things, laying down like architecture for the actual project was super important in the success of the project. The other thing was managing Git. I think we didn't have too many issues with our Git branches in our code base. But that was because of the fact that we definitely focused a lot on handling branches, resolving merge conflicts when we did have them, and looking over any pull requests that we had. The other big thing that we learned was just actually just seeing how big of an impact this application could make in the real world, and that's really it. So here's a live demo of our application. So when you see in the UI, like I was talking previously, was built with Tailwind, and I wanted to add like a raindrop effect to the website, which I think gave it like a nice kind of feeling for the web application, especially tying it into FloodSense. On our sensor map, as you can see, Mapbox has a couple of different integrations. Like we were able to have like a hybrid or satellite or street view of our map, and you were able to see some of our sensors that we had deployed and connected to Grafana, all using HTTPS.